Greetings everybody, and today we're going to be proving the fundamental theorem of algebra using complex analysis. So this states that every non-constant polynomial has at least one root in the complex plane. In other words, the set of complex numbers is algebraically closed. So a couple of years ago, at least for me, this would have seemed like a very big and a crazy thing to prove, but turns out now we have enough machinery and the proof is actually pretty easy and simple. So hopefully this video doesn't go on for too long. But yeah, the main ingredients for our proof will be Liouville's theorem, which is basically how the whole thing works. It states that if f is entire and it's bounded, f is a complex function by the way, then f must be constant. So I've made a video on this in the past. I think it would have been the previous video, so I'll link that in the description below if you guys want to check it out. So yeah, the fundamental theorem of algebra is kind of like the big corollary of this Liouville's theorem. So let's go ahead and get started with the proof. Let's jump straight into it. So how does the proof go? Well, first of all, let's some complex polynomial, let's call it p of z. What does p of z look like? It looks like a n z to the n plus a n minus 1, z to the n minus 1 plus ... all the way down until these lower order terms. So we have a1 z plus a0. Now what do we want to show? We want to show that our polynomial p of z is equal to 0 for some z in the complex plane. Now what I'll do actually is, without loss of generality, so I'll write w log over here, and we're going to assume that an is equal to 1. So in other words, this is a monic polynomial. Now if your polynomial isn't monic, then there's no problem because you can just divide by the leading coefficients and you still get the same thing. This just makes it a little bit cleaner in my opinion. And the way we're going to set this up is we're going to be proving this by contradiction. So by contradiction, well, we want to show that there exists some z in the complex plane such that our polynomial equals 0. Let's assume otherwise. Let's suppose that p of z is not equal to 0 for all z in the complex plane. Okay, so now if this is the case, then let's define a new function. Let's call it f of z, and we'll define that just to simply be the reciprocal of p of z. Now since a p of z is never equal to 0, then 1 over p of z will never blow up. So in fact 1 over p is actually going to be analytic or differentiable everywhere. And yeah, that's quite easy to prove because you can just use, for example, the chain rule for this, and you can differentiate this guy. And since polynomials are differentiable, then yeah, our f of z is also differentiable. So what we know so far is that our function f of z is differentiable for all z in the complex plane. In other words, it's entire, which is kind of like the first condition for Liouville's theorem. So the idea is now we want to use Liouville's theorem to show that our function f is a constant function to arrive at a contradiction. So we've shown one thing, which is that f is entire. Next we need to show that f is bounded. Now there's a couple ways of going about doing this, but I'll present to you guys with this method. It's not as complicated and rigorous as the other ones though, but it gets the main points across. Let's take the absolute value of our function f of z, and we want to show that there's an upper bound for this, which means we want to show that it's less than or equal to some capital M, which is our upper bound. So how do we do this? Well, let's write out what the absolute value of f would be. So this is 1 over the absolute value of z to the n plus a to the n minus 1, z to the n minus 1 plus all the way down until a0. Now what I'll do is I'm going to factor out z to the n. So this is 1 over absolute value of z to the n. Then what's left on the inside? Well, we have 1 plus a to the n minus 1 over z, and then all the way down until we have plus a0 over z to the n. Now I want you guys to notice one thing over here. If we take the magnitude of z to be very large, then what's going to happen is that this second absolute value over here, that's going to approach 1. So this part over here, it's going to approach 1 as the magnitude of z approaches infinity. And you can show that rigorously by, for example, putting bounds on this absolute value, maybe bounding it above using the triangle inequality and bounding it below with the reverse triangle inequality, and you can prove this limit quite easily. But it's pretty clear that this is true because as these z's get bigger, then all these other terms disappear and you're just left with 1. So what this means, we can say that our function f of z, an observation that we can make here is that the absolute value of f of z is asymptotically equal to 1 over the absolute value of z to the n. So for larger values of z, our function f of z, it looks like 1 over z to the n. And what do we know about the function 1 over z to the n? It approaches 0 as the absolute value of z approaches infinity. So if this is the case, then since these are asymptotically equal, then our function f of z, it also approaches 0 as z approaches infinity. So we're doing all of this because I want to come up with a bound for, you can say, the tail end of our function f of z. So because we have this limit over here, we can say for all epsilon greater than 0, so I can pick any epsilon greater than 0, then there exists some radius r greater than 0, such that whenever my absolute value of z is greater than r, my function f of z is less than epsilon. So this is kind of like the definition of convergence from real analysis. If your function f of z approaches 0 as the magnitude of z increases, then for whatever threshold epsilon you pick here, there must be an r such that your function is bounded above by this epsilon. So yeah, epsilon in this case could really be anything, doesn't have to be small or anything. We're just trying to show that the tail end of our function f of z is bounded above by this epsilon. So that was I guess the tricky bit. So we know there exists this r here such that when the absolute value of z is greater than it, we're bounded by this epsilon. Now what happens if the absolute value of z is less than or equal to r? So for z less than or equal to r, what's going to happen? Well, notice, what is z less than or equal to r? This is simply the closed disk that's centered at the origin with a radius of r over here. Now, what do we know? Our function f, we discussed before that was differentiable, and differentiability implies continuity. So by the boundedness theorem, I haven't proved that yet on this channel, but it's a theorem from real analysis that also extends to complex functions as well. If your function is continuous on a closed region, then your function is bounded. So when we're on this closed disk over here, then there exists some upper bounds, let's call it a c, such that our function f of z is less than the c on this disk. So a nicer picture that you can draw out just to see everything in action is, well, let's try to graph out 1 over z to the end. This probably looks something like this, some decaying function like so. And what does your function f of z look like? Well, it can do really anything. It can be as crazy as you want it to be for small values, but for large values, we know that it must kind of follow the graph of 1 over z to the n, so it's asymptotically equal. And since both of those approach 0, then what we did before, we can pick any epsilon greater than 0. So this is the epsilon that I choose here, then there must exist some r here such that my function is bounded above by this epsilon. And how about less than or equal to this r? Well, we know our function must be bounded on this region, on the closed disk. So we're going to have some other upper bounds over here. Let's call that c. So finally, we can let m be defined to be the maximum of c and epsilon. So c could be smaller than epsilon, it could be bigger than epsilon like we have in this picture, it doesn't really matter. And we see that our function f of z is always less than m. In other words, it's bounded by m for all values of z. So if we take a look at Liouville's theorem, we've shown that f is entire and it's bounded everywhere in the complex plane. So therefore f must be constant. So in the end, what do we find? We find that our function f of z, which is also 1 over p of z, is a constant by Liouville's theorem. But this is a bit of a problem because this implies that our polynomial p of z is constant. But this is a contradiction because we clearly defined that p of z to be equal to z to the n plus a n minus 1, z to the n minus 1 plus dot 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 plus a 0, and clearly this is not constant. So that means that our initial assumption was wrong. What was our initial assumption? Well, we supposed at the very start that p of z was not equal to 0 for all z in the complex plane. And since we arrived at a contradiction here, then there must exist a z in the complex plane such that p of z is equal to 0. And then we are done. We've proved the fundamental theorem of algebra. So that's quite nice. So we've done the proof, maybe just a little bit of an extension to this. Since we now know that every polynomial has to have at least one root, that means if we have a polynomial, let's call it Pn, so this is an nth degree polynomial, let's call it Pn of z, then since it has a root, we are able to factor it. Let's factor it into, let's say, z minus, let's call it a1, that's our first root, times another polynomial of 1 degree less, let's call it Pn minus 1. And now this is another complex polynomial, so we can apply the same theorem again, the fundamental theorem of algebra, and this guy factors into, let's say, z minus a2 times another polynomial, let's call it Pn minus 2 of z. And we can keep going with this process until we get to z minus a1, dot dot dot, and then z minus an. And once we arrive at an, well, the polynomial before would have just been a linear polynomial, so this would be the final factorization. So as you can see, there are a total of n linear factors that we get, and if all of your roots here are unique, you actually get exactly n of them. So an nth degree polynomial should factor into exactly n roots. Now you could have two factors that look the same. In that case, that root would have a higher multiplicity, but if you count the roots including multiplicities, then it should be exactly the degree of your polynomial. So this goes up to degree of p, degree of Pn. So yeah, that's pretty much all for this video on the fundamental theorem of algebra. Hope you guys enjoyed it, and I will see everyone in the next one. Bye bye.